Hi there. Today the video is on springs and Hooke's law, a simple topic, extension from GCSE. Now the focus will be more on energy stored in the springs and the non-uniform and uniform deformations. Deformations, yes. Okay, let's just get started. The first one is the meaning of these two words, tensile and compressive. Let me just make two springs here. So if I have a spring, I'm just making a horizontal spring. Okay, so let's say if you're pulling the spring from both sides by force F and the spring extends under the action of this pair of forces, so then the deformation produced is called tensile. Whenever there is an increase in length, it is tensile deformation. And then if you are, instead of pulling the two ends, you try to compress the two ends, the total length would end up decreasing. So if you're pushing it with a couple of force on both sides, the overall length of the spring would decrease. So then say this, see this one, so this here, it is called compressive deformation. So when the overall length decreases. But whatever is the case, there is the change in length, whether it's an increase or decrease, we show the change in length as delta x. Triangle is for change. So change in length x, either in tensile when there's an increase or compressive when there's decrease, is found to be proportional to the force applied. That's your Hooke's law. That is the force is proportional to the extension. So if I remove the proportionality sign, I get a constant K, which then depends on the nature of the spring and is also called as force constant. So it depends on the nature of the spring. So that if you have a very tight spring, the K would be larger. A loose spring, the kind which you have in your pens, would have a less K. The kind of spring which you have in the shock hoops of a vehicle, a car or a motorbike, would have a very large K. So it depends on the nature of the spring and is known as force constant or spring constant. Now, unit, as in any new physical quantity, you would like to know the unit. So if I rearrange this equation, I get my K as force over change in length, and force is measured in newtons, change in length is in meters, so K is Newton per meter. It is of course a scalar quantity because it depends on the nature of the spring. It is a scalar quantity. Now Hooke's law says, now when is Hooke's law not valid? If your body is inelastic or a plastic. So it is important that it should be done within elastic limits. Now why within elastic limits? Is because if it is no more elastic, if you stretch a spring so much that it cannot go back to its original shape, it is no more elastic, and then Hooke's law is not valid. So Hooke's law to be valid, it is important that a spring should be within its elastic limits. Spring, or for that matter, if you have a rubber or a string or any polymer, a wire, anything that when you stretch and you remove the applied force, it comes back to its original length, Hooke's law is valid. You remove the applied force, it cannot go back to its original length, Hooke's law is not valid. Now by doing a setup in the lab, you can add forces on the spring and measure the extension and draw the graph. So if I draw a graph between force on, so force in newtons and extension in meters. I'm just doing it very carefully because this is a graph that you need to know, you need to understand very well. Say if it's a straight line, okay, as long it is a straight line, that means, you know, you have been taught this so many times in GCSE, is directly proportional. Say the minute it stops being a straight line, it has reached its limit of proportionality, and after a little bit after limit of proportionality it reaches elastic limit, and if you keep adding stress it would reach its yield point. After that, a deformation, so a weird deformation. So this here is called limit of proportionality because the line is no more straight after that. So Hooke's law is valid only up to this point, and then this here is called elastic limit. So after this, if you apply force after this, it cannot come back to its original shape. And then this one here is called, let me just make it on this side, please do not, yeah, I'm a little scared. Okay, so this here is yield point, and if you continue applying force even after this point, the spring might break. So this region here up to elastic limit is called elastic deformation. So this one is elastic deformation. Okay, up to this point. And then after this, it is called plastic deformation. It's elastic is something that can regain its shape after removing the forces. Okay, so that's the force extension graph. Now, but what does force extension graph gives us? Two things. Before this, I'm going to just, if it is a force and extension graph, the gradient would give you the spring constant or force constant. Okay, so I'm just taking two types of graphs here. So one is a straight line graph. So the gradient gives spring constant. And area under the graph gives, because you're doing force times extension. What is force times distance? Work done. So work done means energy stored. So whatever work you're doing in stretching the spring is stored as elastic potential energy of the spring. Elastic potential, if there are no losses, of course, energy of the spring. So if Hooke's law is valid, in this case a straight line, almost a straight line, say if it's a straight line, let me just, because this is really important, if it is a straight line, then Hooke's law is valid. Okay, straight line. So now Hooke's law is valid, and what is the area under the graph gives you? This area under the graph will give you energy stored. Okay, now two lines. If I have another line here, Okay, so this one will have higher spring constant because it has higher gradient. All right, so larger the gradient, larger is the spring constant, larger area under the graph, larger is the energy stored under the graph. So this one, now another kind of graph is, let's say here, all right, so just suppose straight line and it becomes a non-Hooke's law. So then just you will have to maybe count the number of the squares or do integration to calculate this area. So this area, what does it gives you? Elastic potential energy. Again, force, and this one is extension. I'm not liking this. I'm just going to make it a little beautiful so that, you know, if it is looking good, you'll remember it more. It's just my theory. It is not some scientific theory. Okay, so only thing is, if it is not this, what I'm trying to say here, if it is not a Hooke's law, you need to find out the area under the graph by either counting the squares or by integration. So I'm just going to make a line here, and this is the area. All right, okay. Now stress, a new term which you have not learned in GCSE. So this is sometimes, not sometimes, denoted by the letter sigma. This is a symbol for stress. You don't need to remember it, just to know. So this is defined as force applied per unit cross-sectional area. Okay, area of cross-section. For example, if you have a wire, okay, let's say you have a thin wire. I'm just going to make a thin wire here. So thin wire, and you're applying the force at one, okay, you're applying the force here. So this is the area of cross section, which will be in this case calculated using pi r square. So you're applying force here F. So because this force is trying to increase the length, this stress would be called as tensile stress. So tensile stress increases the length. Okay, increases the length. So what is the formula for stress? Force over area. Now unit, what would be the unit for the stress? It is Newton slash meter square. And stress, sometimes also called as pascals, is a scalar quantity. I'm thinking, is it? Yes, stress is a scalar quantity, although the force is not scalar, but stress is a scalar quantity. I think so, yeah. Now, can you also have compressive stress? So the compressive stress would be when you're trying to decrease the area. Okay, I'm just going to try and make the diagram. All right, let's say if you have same wire or a rod, less wire is easier to imagine that its length can be increased or decreased. So if you're applying a force here like this and a force here, again, if you're not applying the force on the entire length, you're applying the force on this cross section only. So in the formula for stress, you will take this area. So this would be a compressive stress because it is trying to decrease the length. Okay, so compressive stress, just like tensile stress, would be a scalar, I'm just reluctant, but whatever. You're in A levels now, you can deal with the facts. It is something called as tensor. Okay, so it's neither scalar nor vector. It is something called as tensor because, okay, you go ahead and search why it is not why it's not a scalar, why it's not a vector, because some of you might not be interested in this extra information, so I'm not going to bore them. But if you are, go ahead and search. That's your homework for today. So stress, force over area, unit Newton per meter squared. It could be tensile if it tries to increase the length. It could be compressive if it tries to decrease the strength. Now, strain. What stress does is changes the length. Okay, sometimes this is the symbol which is used to show strain. This symbol is read as epsilon. These are all Greek alphabets. Okay, now strain is defined as change in length over original length. Now, since it's a ratio of the lengths, it has no unit. Okay. If strain is negative, that means it is a decrease in the length. If it is positive, there's an increase in the length. So change in length over original length. Yeah, that's it. So who produces strain? Stress. A tensile stress would produce a positive strain. A compressive stress would produce a negative strain. Ultimate tensile strength. Now consider this. If you have a wire which you are trying to continuously apply a tensile stress and you're trying to increase its length, okay, so let's say it increases its length, so the maximum possible stress that you can apply on it before it breaks, it's called its ultimate tensile strength. So the maximum possible force, if you are stretching a rubber, you're stretching, at the point at which it breaks, the force you have applied at the point where it breaks is called ultimate tensile strength. So tensile, you're trying to increase the length. The force per unit area that is responsible for breaking the wire is called ultimate tensile strength. Okay. Young's modulus, again a new thing. All these are new words. So this is defined for any wire, a gold wire, a copper wire, whose area is fixed. No, not area. Any kind of wire, the ratio of the stress and strain, it remains constant if it is within its elastic limit. Okay, the ratio of stress to strain remains constant, and that ratio is called Young's modulus. Stress over strain, that means if you have a copper wire, the larger stress would produce larger strain because the ratio has to remain constant. If one increases, another increases too, to keep their ratio constant, and the ratio is Young's modulus, and it is noted by capital Y. Now the unit for Young's modulus, strain has no unit because it's a ratio of length. Stress is same as the unit of pressure, Newton per meter square. So the unit of Y is also Newton per meter squared. That's it. Let's do one question. You go ahead, pause it and do it yourself. So you have an original wire of length 2 meters. So I have a wire of length 2 meters. So that's a 2 meter length wire. Area of cross section. So this area is 1 times 10 to the power minus 6 meters squared. Stretched by a force of 200 newtons. So the force that's applied is 200 newtons on both the sides. Extension is 1 millimeter, so change in length is 1 times 10 to the power minus 3 meters, millimeter to meters. Now calculate the stress. Force divided by area. Force is 200 divided by 10 to the power minus 6. This gives me 2 times 10 to the power 8 Newton per meter squared. Strain, change in length over original length. Change in length is 10 to the power minus 3 divided by 2, which is 5 times 10 to the power minus 4, no unit. Young's modulus is stress over strain. So stress is 2 times 10 to the power 8, and this is 5 times 10 to the power minus 12. 5 4s are 20. 4 times 10 to the power 13. No, 11. 11 Newton per meter squared. That's it. Okay. Again, if you're not happy, rewind, try to do it yourself, because 8 minus 4, 12, and then 0.4 times 10 to the 12 is 4 times 10 to the 11. Yeah, that's my answer. Let's check. Yep, that's the answer. All right, okay, I made a mistake. No, I did not make a mistake. So Young's modulus is 4 times 10 to the power 11 Newton per meter squared. Now, elastic and plastic deformations. So again, we draw the graph between stress and strain. We drew the graph between force and extension. We're drawing the graph between stress and strain now. So if it is a straight line here, the gradient would give you the Young's modulus. The gradient up to the elastic region gives Young's modulus. And if you calculate the area for stress and strain, the area is going to give you energy per unit volume. Okay, force and extension was giving you energy, and this one gives you energy per unit volume. Okay, I'm just trying to explain you what's because some of you might be curious here. You don't need to know this for any of your exams. So you're going to calculate area by timesing stress and strain. And what is stress? It is force over area. And then strain is change in length over original length. Now this here is energy. And what is area times length? Is volume. So this is how energy per unit volume. Remember, stress over strain is energy over volume, and force and extension, it is energy. Here you go. Now, different kind of, these sometimes you get 6 markers and 4 mark questions over qualitative understandings of these graphs. So let's just understand here. So sigma is stress and this epsilon is strain. So if you see this one is just follows a straight line and then there's nothing happens. So after this point, if a stress is applied, it breaks. So this is the ultimate tensile strength. It just breaks because it's a brittle material. This one, the ultimate tensile strength is less, but it can have more extension in it. That's why it is ductile. Ductile is a wire that can be stretched into thin wires, right? If you remember key stage 3 definition. So what is happening? This one is a ductile material because although its ultimate tensile strength is less, it can have more strain in it. It can be extended. Now see this rubber, elastic rubber. See this one, way less ultimate tensile strength. A little extra force you apply and it breaks. But then it has such a huge amount of extension, and it is up till the straight line. It is elastic deformation, and now this is plastic deformation. Okay, so that's just the explanation of the graphs. Let's use this question. Explain how the area under stress strain graph is related to the energy stored in a material. So area under stress strain graphs gives you energy stored per unit volume. Why the area is larger for a ductile material compared to a brittle material? Because a ductile material will have more extension, brittle is just going to break. So obviously, because ductile has more extension, it absorbs more energy before breaking. That would have more area. Go ahead, read it, pause and read it. And then this is stress and strain graph of one of the actual body, which was made up of steel in this shape. Now see what's happening here. If you are struggling with so much data, go ahead, pause and try to do it, understand it. Now see the first one. Now this first one is here. Okay, no force is applied, so it's here. The little bit force is applied, so as you can see, there is an extension on this side. So there's an extension, so there is a strain produced, and we're assuming that it is elastic. The minute you remove the stress, it's going to go back to the original shape. So this is elastic strain, and the slope will give you Young's modulus, that is a gradient, stress over strain. Okay, now after this point, because it is no more a straight line, it has started to become plastic. So this is plastic, but the plastic is also its uniform plastic deformation, and then the next part is non-uniform. You will be required to read the graph and understand the graph in all modules, all topics of your A-level physics. So you cannot escape graphs. So let's start understanding it today. So for this, now this here you see this word necking. So can you see here how this part and this part are different? Suddenly there's a small part of this dumbbell shaped body has become really thin. So that thin part is called necking. That means it's about to break. You clearly can understand it's not going to break from here. It's not going to break from here. This is where it's going to break, and then produces a fracture. So fracture, the minute the fracture happens, it no more exists on this graph. Now this entire area here is going to give you the energy stored per unit volume of this body, because it's the area under stress and strain graph. Okay, right, now let's just see. This could be your exam question, so understand what it's trying to say. Two materials have stress and strain graphs. Material A has steeper initial gradient, so I'm just trying to draw here. Okay, A and B, let's just draw here. A has steeper initial gradient. I don't know what's the and this is the B, but fractures at a lower strain. So let's say this one fractures later. So this is A and this is B. So this one fractures here and this one fractures here. What do we have on the vertical axis is stress, and what do we have here is strain. Which material has greater Young's modulus? Obviously, the one has steeper gradient would have greater Young's modulus. Which material is more brittle? The one that breaks earlier. A breaks earlier, has less strain, and hence is brittle. Okay, now what does the meaning of greater Young's modulus means? Because sometimes even that is required in the exam. This means it's a stiff wire. or a stiff material. It is difficult to extend. See, I'll explain you here. So if you have this as, okay, now let me just, we want some good looking graph here. Okay, remember my theory? Something when it looks good, you remember more. Yeah, my theory. Okay, so I have one graph in blue and let's make another graph in purple. So A is stiff. Why is that? To produce this much extension, you require this large amount of stress. But here in the purple, smaller stress as compared to blue, but a larger strain. Hence, it's not that stiff. You need to be using these words in your exam questions. So stiffer, larger Young's modulus means it's stiffer. Then material A fractures at lower strain. That means it is more brittle, and brittle materials show less deformation before breaking. So there is less deformation. A student says a material that stretches more must be stronger. Now, strength comes from stress or strain. Okay, so this is the material, and then this is another material. Which one is strong, A or B? A is strong because it has higher stress. But who has more extension? B, because it goes all the way up till here. This statement may be incorrect because, here you go, the answer. Pause and read. So if it is withstanding higher stress, it is strong. But if it is stretching, it should have higher strain. That means it could be ductile, but it is weaker. Maximum stress before breaking is strength related to ultimate tensile strength. More extension is related to ductility. Okay, so that's it. So it's lots of new words today. You need to just go through it once again, solve some questions from Merit Minds, and if you're struggling with few words, come back again, watch the video, and that's it. That's it for watching. Thank you so much.